The James Webb Space Telescope recently captured a surprising event involving Pluto, the dwarf planet. Pluto's unique orbit, which is inclined at 17 degrees and intersects Neptune's path, brought the two celestial bodies together. This rare scene provides astronomers with an extraordinary opportunity to unravel the mysteries surrounding these distant members of our solar system. Pluto was first discovered by scientists in 1930 and was initially classified as a planet. However, it was later reclassified as a dwarf planet due to its unusual orbit. Despite no longer being considered a full-fledged planet, Pluto continues to fascinate many. It features a thin atmosphere and a bright glow when near the Sun. Some well-known scientists, such as Michio Kaku and Neil deGrasse Tyson, have expressed concerns that Pluto might eventually collide with Neptune. They fear such a collision could occur in the future. Pluto is known for its unique orbit around the Sun, which takes an exceptionally long time to complete, 248 years. Having been discovered in 1930, Pluto has yet to complete its first full revolution. The inner workings of Pluto remain a mystery. It is an outlier in our solar system when it comes to its orbit. Unlike other planets, Pluto's orbit is not a perfect circle, and its trajectory is steep. At certain times, Pluto surpasses Neptune and approaches the Sun, an important occurrence. The scientific community has been puzzled by how Pluto can continue its journey despite its unusual orbit. The reason lies in the various gravitational forces acting on celestial objects. Pluto's orbit has been studied since its discovery, and scientists have tracked its complex path around the Sun. Unlike an ideal orbital plane, Pluto's trajectory is constant as it continues its journey. The motion of Pluto and Neptune around the Sun is part of what is known as the three-body problem, a complex puzzle where scientists attempt to understand the movement and interaction of celestial bodies. This problem describes the motion of Pluto, Neptune, and the Sun, along with their gravitational interactions. Simulations from the late 1980s characterized Pluto's orbit as chaotic, meaning that small changes in its initial conditions could lead to significant deviations in its orbit over millions of years. However, despite the chaos, scientists found that Pluto's orbit remains stable during certain time periods that extend beyond human comprehension. These advanced simulations have helped scientists understand how the gravitational forces of massive planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune and Pluto are unique because they do not belong to either the inner or outer solar system. The phenomenon of orbital libration explains how Pluto always remains at least 90 degrees away from Neptune when it crosses Neptune's orbit. Additionally, the deviation of Pluto's orbit from the ecliptic plane, known as latitude libration, explains why Pluto's orbit is so high above the ecliptic. Pluto only comes close to Neptune or other large planets during specific periods. Pluto is also characterized as having two distinct sides, a soft one and a hard one, that complement each other and provide stability. Scientists using virtual simulations discovered that the greatest deviation in Pluto's orbit from Neptune occurs every 20,000 years due to a 3:2 orbital resonance. This resonance means that Pluto orbits the Sun twice for every 3 orbits completed by Neptune. The gravitational pull of the Sun stabilizes Pluto's orbit over time. Jupiter and Saturn also influence Pluto's orbit. Jupiter's gravity plays a significant role in keeping Pluto's orbit stable, while Saturn contributes to the small ring system near Jupiter. These findings reveal that Pluto can maintain a relatively stable orbit over billions of years thanks to the gravitational forces exerted by these larger planets. Without such forces, cosmic order would be disrupted, and the system would become unstable. If two celestial bodies were to collide or deviate from their paths, it could lead to chaos in the universe, as is the case with Pluto. Predicting celestial events, especially those involving planets with irregular orbits like Pluto, is inherently difficult. The behavior of such systems is unpredictable, which is why long-term forecasts are avoided. While Pluto has one of the most unstable orbits, it remains a crucial focus for scientists. It serves as a reminder of the ever-changing universe. Some scientists, who have staked their reputations on the possibility of a Pluto-Neptune collision, admit that while their relationship is complex, a collision could still occur. This idea raises questions about whether a crash between these two celestial bodies is even possible. Neil deGrasse Tyson, a prominent scientist and advocate for space exploration, has provided insights into the secrets of our solar system and played a key role in Pluto's reclassification. Tyson sees Pluto's orbit as an example of the vastness of space yet to be explored. He believes that Pluto's peculiar orbit adds to the allure of astronomy and sparks curiosity about the universe. Tyson warns the public about the potential dangers of Pluto's unusual orbit. A collision between Pluto and Neptune would likely create a massive shockwave that could slightly warm Pluto's surface. Due to Pluto's small size and mostly frozen state, the collision could release a tremendous amount of energy. Material from the impact could be ejected into the outer reaches of the solar system, potentially affecting nearby planets and their moons. However, the immediate impact on Earth would be minimal, as the outer solar system is relatively far from our planet. The scientific implications of such a collision, however, would be immense. A powerful telescope might even temporarily increase Neptune's brightness to the point where it could be seen with the naked eye from Earth, appearing as a faint star. Similarly, physicist Michio Kaku described how such an event could tie into his ideas about the universe. He believes that a collision between Pluto and Neptune would be an astrophysical event, something that might happen only once or a few times in the history of the universe. Such events challenge our understanding of string theory and the vastness of space. In comparison, the TRAPPIST-1 system, a group of 7 Earth-sized planets, follows patterns due to their gravitational interactions. While these planets could potentially collide, their orbits currently prevent any accidents. Scientists continue to monitor these planets closely, studying how their movements influence each other. The study of Pluto's orbit and its interaction with other celestial bodies in the solar system is not only crucial for understanding the dynamics of our local cosmic neighborhood, but also offers insights into broader astrophysical principles. While Pluto's orbit is often considered chaotic, scientists have made significant progress in understanding how such chaotic orbits can still exhibit periods of stability. One key to this stability lies in the orbital resonance between Pluto and Neptune. This resonance ensures that although the two planets' orbits cross, they never actually collide due to the precise alignment of their movements, which prevents close encounters. Despite the apparent chaos, the phenomenon of orbital resonance, specifically the 3:2 resonance between Pluto and Neptune, is a fascinating aspect of planetary dynamics. This resonance means that for every 3 orbits Neptune completes around the Sun, Pluto completes exactly 2. This relationship ensures that Pluto and Neptune are never in the same position at the same time, even though their orbits intersect. The gravitational influence of Neptune on Pluto is significant, but the resonance precisely keeps Pluto's orbit from being threatened. This kind of gravitational dance is a common feature in many areas of the solar system, where the gravitational influence of one body helps maintain the orbital integrity of another. However, the interactions between celestial bodies like Pluto, Neptune, and the Sun are not limited to simple orbital mechanics. The vast distances between planets and their complex gravitational interactions lead to various phenomena that are still not fully understood. One such phenomenon is the peculiar orbit of the dwarf planet Haumea, another member of the distant solar system that is sometimes compared to Pluto. Haumea's orbit is even more erratic than Pluto's, and studying its movement could provide further insights into the gravitational forces that govern the outer reaches of the solar system. As astronomers continue to observe Haumea and other trans-Neptunian objects, the similarities and differences between these distant worlds and Pluto may yield new discoveries about the formation and evolution of our solar system. Another important aspect of studying Pluto is its role as a representative of the Kuiper Belt, a vast region of space beyond Neptune that contains numerous small icy bodies. The Kuiper Belt is home to many dwarf planets, comets, and other objects, and its study has become increasingly important in understanding the outer solar system. Pluto is one of the largest known objects in the Kuiper Belt, and by examining it, scientists gain insights into the conditions and processes that occurred during the early stages of the solar system's formation. The Kuiper Belt is believed to be a remnant from the solar system's formation, containing material that never coalesced into full-fledged planets. The study of Pluto and the Kuiper Belt also opens the possibility of considering other trans-Neptunian objects in our quest to understand the solar system's outer reaches. In addition, Pluto's orbit provides a fascinating example of how complex and dynamic celestial mechanics can be. The interactions between Pluto and Neptune, along with the influences of other planets like Jupiter and Saturn, illustrate the delicate balance required to maintain orbital stability. Despite its chaotic and eccentric orbit, Pluto's long-term trajectory remains relatively stable, thanks in part to gravitational resonance with Neptune. This phenomenon highlights the intricate nature of planetary dynamics and the ongoing need for astronomers to refine their understanding of the forces at play. While Pluto may no longer be classified as a planet, it remains an essential object of study in planetary science. Its eccentric orbit, unique characteristics, and role in the Kuiper Belt make it an invaluable target for research. By continuing to observe Pluto and its interactions with other celestial bodies, scientists can learn more about the processes that shape our solar system and the larger universe. The mysteries of Pluto's orbit and its place in the broader cosmic picture continue to captivate astronomers, and new discoveries are likely to emerge as technology advances and our understanding deepens. Pluto's significance extends beyond its unique orbit and classification. Its surface composition, atmosphere, and potential subsurface ocean make it a subject of interest for understanding the diversity of planetary bodies in the solar system. Observations by the New Horizons spacecraft in 2015 revealed stunning details about Pluto's surface, including vast plains of nitrogen ice, towering water ice mountains, and evidence of geological activity. These findings challenge the notion that small, distant bodies like Pluto are geologically inactive and unremarkable. One of the most intriguing features of Pluto is Sputnik Planitia, a heart-shaped plain composed largely of nitrogen ice. This region exhibits patterns of convection and resurfacing, indicating that Pluto may have an internal heat source. Some scientists hypothesize that this heat could be generated by radioactive decay or tidal forces from its largest moon, Charon. The potential for a subsurface ocean beneath Sputnik Planitia has also been proposed, raising questions about the possibility of life in such extreme environments. Charon, Pluto's largest moon, is another fascinating aspect of the Pluto system. With a diameter over half that of Pluto, Charon is unusually large compared to its parent body, and the two are sometimes referred to as a binary system. The gravitational interactions between Pluto and Charon are unique, causing both bodies to always show the same face to each other, a phenomenon known as mutual tidal locking. Charon's surface, marked by deep canyons and a dark polar cap, suggests a complex geological history that complements Pluto's own. Beyond Pluto and Charon, the Kuiper Belt harbors many other intriguing objects that offer clues about the early solar system. Eris, another dwarf planet, rivals Pluto in size and has a highly reflective surface, likely due to a layer of methane ice. Makemake and Haumea, with their unique shapes and characteristics, further illustrate the diversity of objects in this distant region. By studying these bodies alongside Pluto, astronomers can piece together a more comprehensive picture of the Kuiper Belt and its role in the solar system's evolution. The exploration of Pluto and the Kuiper Belt also has implications for the search for planets beyond our solar system. Understanding the dynamics, composition, and behavior of distant objects like Pluto can inform studies of exoplanets in other star systems. For instance, the discovery of icy worlds in the outer reaches of the solar system has parallels with the icy exoplanets identified in the habitable zones of other stars. These comparisons deepen our understanding of planetary formation and the potential for life elsewhere in the universe. As technology advances, future missions to the Kuiper Belt could reveal even more about its composition and history. Proposals for spacecraft to revisit Pluto and its moons, or to explore other Kuiper Belt objects, are already under consideration. These missions could address unresolved questions about the formation and evolution of icy bodies, as well as the processes that shape the solar system as a whole.